Hello. We're live. We should be live. Toot 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 toot. Give me 1 minute to grab some coffee and let people show up. I'm so tired. Be right back. Hey, I'm back. How's it going? Anyone watching this? Someone's watching this. How are you doing? So, what's happened? I got homework posted on Wiley Plus. I got the next week of stuff. I guess I should go ahead and post all the rest of it. I know some of you guys are living off of 2-week free trials. And I guess I'll post the rest of it, and maybe you can get through the rest of the homework by the end of next week. I'm almost at the place where so I taught 122 in the spring, and we are almost at spring break of 122, which is where, coronavirus happened and I started doing everything online. So I already have videos. I'm going to be reusing my spring videos starting pretty soon. When I taught in the spring, I didn't use Wiley Plus. I was using my own homework thing. I'd gotten sick of Wiley Plus, and if I knew about this, I probably would have. But so those lectures are written not addressing Wiley Plus in particular, but I haven't really changed that part of the course, so I think they are just fine. But I will be available daily for questions. I think I will just link to those videos, and then I will show up daily around to say, hey, if anyone has any questions, let me know, and I'll start streaming and do problems from Wiley Plus if you guys want them. I gave the exams back. Oh, someone asked me to review the exam. Let's review the exam. Is this the exam? Yeah, summer 2020. Let me see if this works. Can I print this to... This does not work. Let's just do screenshotting then. Here. No, let's not print it. No, I just closed the whole window. Nope. Let's teach folder 2020 summer 122. Take home exam 1. There we go. There. Snip tool. New snip. Here's a graph of a function. Oh, I need to flip my computer around. Hang on. Go here. Rotate. There. And here. And okay. Let's... No, don't email it. No, I don't... I just clicked the wrong thing. There we go. Here's a problem from the exam. I want to estimate f prime of 20. F prime of 20 from a graph, the easiest way to explain the derivative is as slope of the tangent line. Here's at 20. I hold up a ruler or the other edge of the paper or whatever. Try and draw a line that is tangent at that point. The thing I draw never actually hits the point because my stylus is off by a little bit. Can I slide that up? There we go. So there's a line that hits the graph at 20 and just grazes the curve. It's going the exact right direction. I want to estimate the slope of this line. I grab 2 dots. I like it if they are kind of far away from each other. Ooh, here's a good place where it actually hits a coordinate pretty well. It looks like f prime of 20 is the slope of that line is about, this point is 41, 12, and this point is 15, 32. Difference of the y's over difference of the x's. 20 over 15 minus 41 is negative 26. Negative 20 over 26 is... 0.76, so I'm getting negative 0.76. I'm getting a negative number that corresponds with I can see the graph is decreasing, so that's good. It's not super steep, so I don't have a big negative number. It's smallish. Yeah. There's number 1. What's number 2? Number 2 is this thing. I want to estimate d prime of 2. I look at 2, I say how close can I get to 2? 0 and 4 are tied for closest. I try and find d prime of 2 both ways and split the difference. Difference of the y's divided by difference of the x's. This is if I use 4. 3 over 2 is 1.5. If I do it using this way, I'll get 22 minus 26 over 0 minus 2. That'll be negative 4 over negative 2 is 2. 3 halves is not 1.7, it's 1.5. Splitting the difference between these, d prime of 2 is about, the average of these two numbers is 1.75. What's up with number 3? How steep are these steepnesses? Arrange these from least to greatest. Each of these is the slope of something in this picture. F prime of 2 is the slope of the tangent line at 2, so that's, this point is this steepness. F prime of 5 is the slope of the tangent line at 5, so that's this steepness. This one's A, this one's B. C is f prime of 10, so that's the tangent line here is this steepness. That's C. D is a difference quotient. The slope from 2 to 5 is, let's switch colors so I don't mix these up. Here's 2 and here's 5. So that's this steepness. E is from 8 to 5, so from 5 f of 5 to 8 f of 8 is this steepness. I want to arrange these from least to greatest. Which of these is the most negative? I think this is the steepest downwards, right? Yeah, so this is B is the least. Then it's the blue and the red. The red is steeper. So it's the more negative of between the blue and the red. I didn't label these. The blue one was D and the red one was E. So I think it's B, E, D. Then I have A and C, A and then C. Is this... I need to go back and look at how I graded it. I feel like I was doing something different than that. Oh, here's my piece of paper I was looking at. I may have graded you guys wrong. Let me see if what I graded... I don't remember B-E-D-A-C. I would have remembered that it spelled bedac. I don't know. I'll take a look. Number 4. What's going on with number 4? It's one of these matching doodles. Here's this function. What's the derivative? It's one of these. This thing is decreasing concave down. That means its derivative is negative and decreasing. It's a small negative number, then a big negative number. Which of those graphs on the right is always negative but starts out small and ends up big negative? That's this one. That's D. Is the one that is small and negative, then big negative is D. D. What's up with number 2? Number 2 is decreasing, then increasing, then decreasing. So I want a derivative that is negative and then positive in the middle and then negative. B is the only one that does that. B. What's up with number 3? Number 3 is always increasing, always concave up. So its derivative is going to be positive and increasing. Your small positive number, then big positive number. Which of these is always positive and increasing? That's E. Number 4 is decreasing concave down, the exact same as number 1. So its derivative will be D for the same reasons. Small negative number, big negative number. What's up with number 5? Number 5 increases for a little bit at the start, and then decreases after that. So I'm looking for something that is positive, and then negative, switching close to the left edge. Which of these is positive and then negative? It's this one, so that's G. Number 6 is always increasing, and it's always increasing at the same rate, so it's going to be positive and flat. F is the thing that's positive and flat. I think everyone got that one. So it was DBE, DGF. What's number 5? F is asking, is the function positive or negative or 0 at each of these points? We are above the x-axis, so that's positive. We are above the x-axis, so that is positive. We are on the x-axis, that's 0. What's up with f prime? Are we increasing or decreasing? We are flat, we are decreasing, we are increasing. So that's 0, negative, positive. The third one's asking about concavity. At this point, we are definitely concave down. At this point, we are definitely concave up. At this point, I think this is the inflection point. We were doing that, and now we're doing that. So I would put a 0 here. If you put something else, that is okay if your answer to the second part of the question corresponds with it. The function appears to have an inflection point. Where is it? I put that the second derivative equaled 0 at 7, so I'm thinking it's at x equals 7. If you thought the graph was concave up at 7, that means you must have thought the inflection point was further to the left. That's fine if you put something a little left of 7. If you thought it was still concave down at this point, that's fine if you think the inflection point is a little to the right of 7. Yeah, those are all fine. This is not the inflection point. This is not the inflection point. The inflection point is where do you switch the concavity, which is 7 or somewhere near 7. What do I got for number 6? I got too many. I'm going to close some of these windows. Don't save. Don't save. Don't save. Don't save that one. Yeah, here's the one I want. Cool. It's the cost revenue junk. Let's talk about cost revenue junk. At a production level of 5,000, I know my total cost is 4,800, my total revenue is 6,900, my marginal cost is 2.3, and my marginal revenue is 2.8. I can turn all these into mathematical statements if I want. C of 5,000 is 4,800. R of 5,000 is 6,900, so that's nice. MC of 5,000 is 2.3, we got that going on. And MR of 5,000 is, what was that, 2.8? This is supposed to be a 3. What is this asking us? A is, what's my profit? Profit is revenue minus cost is 6,900 minus 4,800 is 1900. No, I can subtract. 2100 dollars is the units. What's my marginal profit? Marginal profit equals marginal revenue minus marginal cost. That was our first rule of derivatives, is that if this equals this minus this, then the derivative of this equals the derivative of this minus the derivative of this. Marginal revenue minus marginal cost is 2.8 minus 2.3 is $0.5 per unit, are the units on that. Estimate my revenue at a production level of 5,500 units. This is the new Y value, new old Y value thing. My new R value, I can be estimated by taking my old R value plus the rate of change times the change in Q. I guess my rate of change would be dr dq here. What's my old R value? I know what the revenue is at 5,000. I know what the derivative of revenue is at 5,000. And I know how much you want to change it by. You want to go from 5,000 to 5,500. That means you're trying to increase by 500. Our prime of 5,000 was 2.8. And my R of 5,000 is 6,900. So this is going to be 6,900 plus 2.8 times 500 is 1,400? Yes, 1,400. Add that on to 6,900, you get 8,300. That's our best estimate for what revenue will be after an extra 500 units. What's up with number 7? Let's go back to zooming in. We're using a difference quotient to estimate q prime of 3. Notice we can just take the derivative of that function. The derivative of the function is 3x squared. So q prime of 3 is going to be 3 times 3 squared is 27. Our answer better be 27, but this is not what the problem's asking us to do. We can use that to check our work, but the thing that they're asking us to do is to find q of a number very close to 3. Let's call it 3.0001 minus q of 3. Divide that by 3.0001 minus 3. I want 3.0001 cubed minus 10 is our first part, minus 3 cubed minus 10 is our second part. Divide that by 0.0001. I get what is 3.0001 cubed minus 10, close the first part, minus 3 cubed minus 10 I can do is 27 minus 10 is 17. Divide that by 0.0001. I get, yes, a number really close to 27. Show enough work to justify why I think 2 decimal places are accurate. Well, okay, this doesn't count as doing enough work, but so far I have a number so close to 27 it would be a miracle if it's not 27, but let's stick in another 0 and double check that those numbers aren't changing. I can hit second enter and change that 00001 to 00001. Oh. Divide that by 0.00001. I get 27 point, this time with 4 zeros. Looks like q prime of 3 is about 27.00. Also, say the equation of the tangent line. It's going to be y equals y value plus the slope, x minus the x value. The y value is, what is q of 3? 3 cubed minus 10. We worked that out somewhere along the way, was 17. plus the slope, that's the derivative, we got that, times x minus the x value is 3. There's the slope of the tangent line. You can simplify if you want it in y equals mx plus b form. I didn't ask for that. This answer's fine. What's going on with number 8? I want to estimate f prime of 1, where f of x is this. F prime of 1 is about f of, I want a number close to 1, and they told me to use delta x is 0.04. That's telling us what number close to 1. Delta x is how much are you wiggling the x value by? They're telling us to wiggle it to the right by 0.04. So it's going to be 1.04 is our number close to 1. So this is going to be 3 to the 1.04 plus 1.04 is how you plug 1.04 into this formula, minus 3 to the 1 plus 1 over 0.04. This number I can do is 4. So I need to ask my calculator, hey calculator, what is 3 to the 1.04? Oh, I wrote divided by 3 to the 1.04 plus 1.04 minus 3 plus 1 is 4 itself. Now divide this by 0.04. I'm getting 4.3693. F prime of 1 is about 4.3693. And I don't want to repeat with smaller and smaller values because they only told us to use this one delta x value. So this is the exact answer this one's looking for. This isn't even an approximation, or this is the approximation they told us to get. Oh, excuse me. What's up with number 9? Here's f of 4 is 21, f prime of 4 is negative 0.3. Approximate these two things. This is the same new y value, old y value. F of 4.2 is going to be about f of 4 plus f prime of 4, 4.2 minus 4. F of 3.95 is going to be about f of 4 plus f prime of 4 times 3.95 minus 4. This thing is 21 plus negative 0.3 times 0.2. 0.2 times 0.3 is 0.06. 21 minus 0.06 is 20.94. This one is 21 plus negative 0.3 times negative 0.05. It's going to be 21 plus, the two negatives make a positive. 3 times 5 is 15. Move the decimal back 1, 2, 3 times. 1, 2, 3, 0.05. I get 21.015. This is f of 4.2 is about that. This is f of 3.95 is about that. I was told to clearly label which answer is which. Number 10, what's going on here? I got a bunch of questions. Let's put them up. Oh. Differentiate these. Derivative of this. 4x cubed minus 1 over x plus derivative of 3 to the x is ln 3 times 3 to the x minus derivative of this is 16x to the 1 minus, this one I need to rewrite, this is 2x to the negative 1, so the derivative of that is negative 2x to the negative 2 plus this one is x to the 1/2, derivative of that is 1/2 x to the negative 1/2. How about this guy? First part's a product rule. Derivative of the first times leave the second part alone, plus leave the first part alone, derivative of the second, minus derivative of x is 1. I can't stay awake. I'm fading, guys. CDE. Okay, this is a quotient. I need to use the quotient rule. Quotient rule says derivative of the top. Now I look at the top. What's the derivative of that? Derivative of 3 to the x is ln 3 to the x. Derivative of cosine x is negative sine x. 2 stays out front. That's all derivative of the top needs parentheses. Times leave the bottom alone. 3x squared minus 4. Minus leave the top alone. 3 to the x plus 2 cosine x. Times derivative of the bottom is 6x. I might put 6x minus 0 to remind myself I did that. All over the old bottom squared. This one is a product, needs a product rule. Derivative of the first, leave the second part alone. Plus leave the first part alone, derivative of the second. Done. This guy is a bunch of chain rule stuff. Derivative of q prime of x. Don't write the q of x equals its derivative. Derivative of this is derivative of 3 to the x is ln 3 times 3 to the x. Derivative of minus cosine something is minus negative sine something. Sine what? Sine leave the inside alone. Times derivative of the inside is 2x minus 8. Plus now I need the derivative of this. This is something to the fifth. Derivative of something to the fifth is 5 something to the fourth. 5 what to the fourth? 5 leave the inside alone to the fourth. Times derivative of the inside goes outside. Cool. There's CDE. This one is saying find the derivative directly. Oh, I forgot to put the function. What was it? I gave you guys... I forgot to put the function and then I texted it to you guys during the test. What did I say? It was f of x is x cubed plus 2x. What's the derivative of this? Power rule says it's 3x squared plus 2. F prime of negative 2 then is 3 times negative 2 squared plus 2 is 3 times 4 plus 2 is 12 plus 2 is 14. So I did that, and then we also want the tangent line. Tangent line is y equals y value plus slope x minus x value. My y value is f of negative 2, which we never worked out. It's negative 2 cubed plus 2 times negative 2 is negative 8 minus 4 is negative 12. The slope is the derivative we found is 14. X minus the x value is negative 2. Comes out x plus 2 because I'm subtracting a negative. We can clean that up for mx plus b if we want to, but we don't care. Was that the last one? It was not. We need a second derivative. What's the derivative? 5 times 3 is 15, x to the 4. Derivative of log x is 1 over x. Derivative of 2 goes away. This thing is x to the 1/3. Derivative of that will be minus 1/3 x to the 1/3 minus 1 is negative 2/3. Now the derivative of this. 15 times 4 is 60, x to the 3 minus 1 over x, that's x to the negative 1. Negative 1 falls out front, makes it positive, x to the negative 2. Negative 2/3 times negative 1/3 makes positive 2/9, x to the negative 5/3. There's our second derivative. That's the exam! The grades weren't amazing, but they were fine. If you're stressing over your grade, don't stress. I mean, if you bombed it, then you bombed it. Yeah, let's just keep moving forward. Homework's posted for the next set. I guess after class I will post the rest of the homework for the year, so if you're hoping to run through the free trial, you can try and do that until 2 weeks after whenever you signed up. And yeah, usually, so when it's not coronavirus time, when I teach this, I give a thing called a gateway exam, is what we would be doing about now. The gateway exam is an exam I give that is just 10 things you need to write down the derivative. You need to get the derivative exactly correctly, or it's 10 problems, they're all right or wrong. If you get 8 out of 10 correct on the gateway exam, then you get 100. If you get fewer than 8 out of 10 correct, you get a 0. And you get 5 attempts. And it's just sort of this way to build up pressure that you need to be getting derivatives correct, or the whole rest of the year is going to go real bad. And I don't see a way to do that in a way that's, it's good for the class because everything that happens going forward is mostly going to bank on knowing how to take derivatives. I can't really give you guys a gateway exam, but you need to, every mistake you made in this number 10 part, try and focus on those. If you're not getting the product rule right, focus on getting the product rule right as we go forward. Focus on the quotient rule, focus on the chain rule. You want to be getting these things right because pretty soon we're going to be doing much, much bigger problems, the very first step of which is take a derivative. And if you're messing up those derivatives, then you're going to be messing up huge problems that you just never gave yourself even a chance on. Yeah. Let's see. Let's move along to... Yeah, let's get into the Chapter 4 stuff. So in Chapter 3 we learned how to look at a function and write down its derivative. Chapter 4 is why do we care? It's applications of derivatives. It's problems you can solve. Now that you know how to write down the derivative of a function. And a lot of this boils down to, we got some word problems coming up. Let's do a real quick example. If I write down this function f of x equals 2/3 x squared minus 8x minus 8/5. You can look at this function, you know enough algebra to say, hey, this is quadratic. It's the kind of quadratic that I don't really want to factor because it's got fractions on there, but maybe I could if you forced me. I know that it's got an a value as positive, so it opens upwards. The graph is going to be a parabola. It opens upwards, something like this, or maybe like this, or I don't know where the parabola is. But wherever it is, it's an opening upwards parabola, which means it's got this point called a vertex. And a question you might have had to answer in your algebra class is, where is the vertex? And you might have had to do this in a couple different ways. Either your teacher gave you a formula about a negative b over 2a, or if you're very unlucky, they made you learn how to complete the square, which is really bad, that is no fun at all. And the thing I want to illustrate right now is finding the vertex has sort of immediately become a real easy question. My function is this. like looking at the vertex and thinking about derivatives, what can I tell about the derivative at this point? Well, hey, the derivative equals 0 there, right? The place where you have your minimum is the place where you're turning around between decreasing and increasing. You're not decreasing anymore, so your derivative's not going to be negative. You're not increasing anymore, so your derivative's not going to be positive. Your derivative has to be 0. And I can see, if I drew the tangent line, it would be horizontal. You'd be like bouncing off of the tangent line, or I guess bouncing would be like hitting it at an angle and then bouncing off, reflecting that angle or whatever. But you're just grazing the tangent line that's a horizontal line. You've got a slope of 0. And hey, I'm really good at finding derivatives. What's the derivative of that function? Derivative of that is 4/3 x to the 1 minus 8. The last part goes away. You're asking me, when does that equal 0? Well, that's a real easy equation to solve. 4/3 x equals 8. Multiply both sides by 3/4. I get x equals 6. There's the vertex. There's the x-coordinate of the vertex, at least, and I can find the y-coordinate by plugging that number into the function, depending how hard it is. This thing that was hard and needed completing the square or something in algebra has become super easy. A lot of what's going to be happening in Chapter 4 is going to boil down to taking the derivative of something and setting it equal to 0, and like we did just now, that's going to be the main... the upcoming exam, if you just took the derivative of everything and set it equal to 0, there's a good chance you get a 50 without knowing anything else going on. Before we get to just doing that, though, let's talk about... let's do some terminology. A problem we like to have is going to be optimization problems. I've got some function, and I want to know, when does it have its minimum? When does it have its maximum? This problem has a local minimum here. The word local is the way you would talk about a local hero or a local track star or something. It's not the minimum of the function, but in the local area, it is the minimum of the function. By in the local area, we mean if you move a little bit to the left or the right, in some small neighborhood, the math word we use for this is neighborhood, in some neighborhood of this point, it would be the very lowest of the graph. If you only look in this neighborhood, he would be the smallest point in the universe. I am not the tallest person in the world, but occasionally I am the tallest person in the room. That would be a local minimum. This one's not the global minimum, because there's a lower point over here. For this graph, this is the global minimum. Which is also a local minimum. This graph has a local maximum. It has no global max because it goes up to infinity. So the thing we want to observe is, hey, looking at this picture suggests that every local minimum and every local minimum, every local maximum can be found because its derivative equals 0 here. That trick we just did mostly works to find all local extrema. It does not always work, though. Here's an example that shows off all the other things that can be going on. I have a point. Zoop, zoop, zoop. Zoop, zoop, zoop. Something like this. It's not always the case that the derivative equals 0 at a local min or a local max. This point, most people would call this a local max. Even though f prime is not 0 here. Here I have a local max. This point, this is an end point of the domain. You should know from your algebra class that the domain is what are the numbers you're allowed to plug in. This is the first number we're able to plug in. You don't have to turn around to be the lowest point if you're here. If you just start going upwards, then that starting point was a local minimum. If I look at some local neighborhood, all the nearby points are below it. Or this one's a maximum, not minimum. This is a local minimum. The derivative doesn't equal 0 here. The derivative is undefined here. These are the two exceptions that can happen. Here I have a local minimum where the derivative equals 0. Here's a local maximum where the derivative equals 0. Here's a local max where the max equals 0. Local min where the derivative equals 0. Here's a local max that's another endpoint. This endpoint and undefined are the types of exception that exist. So, not every local extremum, local max, local min, we can call that a local extremum or a local optimum. These are words we use that mean max or min. Not every local max min has y prime equals 0. The alternatives are it could be an endpoint of the domain, it can be a place where y prime is undefined. And these are the only alternatives. I should have started writing this sentence like this. The fact is that if y equals f of x has a local max or local min at a point, excuse me, then let's say at a point comma a, let's give a name to that point, then f prime of a equals 0, or f prime of a is undefined, or a is an endpoint of the domain. There's only three possibilities. If I'm looking for the local maxes and mins of a function, I just need to say, hey, when does the derivative equal 0? When is the derivative undefined? What are the endpoints of the domain? The only points that could be local maxes and mins are these. But none of these guarantees. Guarantees doesn't start with a Q. None of these guarantees that the point is a local max or min. Your derivative can be undefined. If my graph becomes goes vertical for a second, here's a place where the derivative is undefined. The tangent line doesn't have a slope. Its slope would be infinity. But it's not a max. An endpoint of the domain is almost always a local max or local min. I can come up with examples where it's not, though. They're like sort of pathological if you keep going up and down, up and down, up and down. So I'm approaching it both from above and below. I can write down a formula for a function that looks like this. You won't learn much from it, but like a graph can be really weird like this. This is a place where it's an endpoint of the domain, but it's not a max or min. The bigger one we care about is y prime equals 0. Doesn't guarantee a local max or min. The best example I can come up with, I can draw you one, is if I graph y equals, let's make it x minus 3 cubed plus 2. Go with standard zoom. What did I did? Oh, I forgot there's supposed to be a 3 there. X minus 3 cubed plus 2, if I graph this, it's increasing. It flattens out. There is a point right here at 3 where the derivative equals 0. This is y equals 2 plus x minus 3 cubed. You could take the derivative of this using the power rule and the chain rule and plug in 3 and get that y prime of 3 equals 0. It looks like y prime of 3 equals 0. Like it's moving completely sideways. I often imagine this is like a stop sign graph where I'm driving forwards, I come up to a stop sign, I stop, I am moving 0 miles per hour for exactly 0 seconds, and then I resume moving forwards again. If I covered up this part of the graph and just showed you, you might assume, oh, we're about to turn around, but we don't turn around, we keep moving forward. The derivative can equal 0 even though it's not a max or a min. This is called a stationary point. A place where the graph is traveling horizontally, but it's not going to turn around afterwards. Okay, so and our big terminology. To find, so a local max-min will only happen when we're at an endpoint when y prime of the number equals 0 or y prime of the number is undefined. Well, the endpoints we sort of handle separately. Points with this property, a number a with the derivative equals 0 or undefined, and when I say the derivative is undefined, I'm assuming the original function is defined. Like if I can draw a function that doesn't exist at a point, the derivative will also not exist at a point, but I don't want to call that a critical point. Not because it's not critical, more because it's not a point. There's no dot for me to graph there to ask whether it's a max or a min. These are called critical points. And really the emphasis is on the derivative equaling 0. I'm mentioning the derivative being undefined mostly as a technicality. It doesn't show up in our class. It would show up if we were in a heavier calculus class where we were dealing with grosser functions. You can sort of see when I drew an example where the derivative was undefined. Regular functions that you graph don't really look like this. Like, it's hard to come up with an example that does that. You need an exponent of 2/3 or something can make that happen. If you graph y equals x to the 2/3, by the way. I guess I can graph that real quick. Let's graph x to the 2/3. I'm decreasing slowly, faster, boom, 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 boom. This one doesn't look that nuts, but I can see if I zoom in at 0, 0, it's decreasing down to vertical at that moment. Boy, this is hard to see. You gotta zoom in like crazy to... It looks like it's going down at like a 45-degree angle or something. It's actually going down at an infinite angle if I zoom in enough. Wow. This is really hard to see. One more. Yeah, every time I zoom in, it seems to get steeper. And it's getting steeper and steeper. As I get closer to that point, it's falling down to a straight vertical cutoff and turns around and bounces. And that's the kind of thing I was trying to draw there. That's called a cusp. It shows up from fractional exponents, and we're probably done talking about that for the whole rest of the year. The thing we mostly care about is when does the derivative equal 0. Let's do an example. I'm going to write down this function, f of x equals x to the 4th times 3 minus x to the 5th. Hey, if you are watching this not live, pause the video, take the derivative of this function. You need to be getting these derivatives right. See if you're able to get this derivative right, because you don't want to be wasting a lot of effort on things where you're still getting derivatives wrong. To take the derivative of this, this is x to the 4th times 3 minus x to the 5th. This needs the product rule. The derivative is derivative of the first, 4x cubed, times leave the second part alone, plus leave the first part alone, x to the 4th, times derivative of the second part. The second part is stuff to the 5th. The derivative of that is 5 stuff to the 4th. What is my stuff? I leave the inside alone. And then I multiply by the derivative of the inside goes outside. What's the derivative of the inside? It is -1. Did you catch that negative sign? That's the thing people mess up. My favorite way to teach this section is to ask the class to tell me the derivative, and then have them think it's a positive one here, and go through the whole stupid problem, and then at the very end say, oh, we forgot a negative. This is why I make you pass a gateway exam. I get this. I'm going to want to set this equal to 0. Setting these things equal to 0 is often a huge hassle. The good news is you've almost got it factored. Like the way the product rule spits these things out tends to be in a way where there's largely, we've got two things added up, this plus this, and they have a lot of common factors. Factoring out those common factors... Oh, I didn't even write down the problem. I wrote down this function. Our problem is find the critical points. We're going to do more after that. What are critical points? They are where f prime equals 0. Or, technically, it's also where f prime is undefined, but f is defined. But these are never going to happen. I'm just going to keep mentioning them because they're technically part of the definition, and I feel bad if I say a thing that's not true. I want to know when the thing equals 0. I'm going to want it factored. It helps me to look for common factors and pull those out of these two terms. You've got an x cubed, and you've got an x to the 4th. That means I can pull x cubed out. You've got 5 3 minus x's, and you've got 4 3 minus x's. The thing you have in common is 4 3 minus x's. I will factor all of those out. What's left if I factor all this chunk out? This part has a 4 left over. All the x cubes are gone. One of these 3 minus x's is left. Plus, what have you got left? 3 of those x's are gone, but there's 1 left over. The 5 is still there. We didn't pull that out. All of these things are gone. The -1 is still there. So this thing in the brackets is actually not that complicated. You got x cubed, 3 minus x to the 4th, times, this is 12 minus 4x, this is minus 5x, I get 12 minus 9x. If I'm crazy about factoring, I can also factor another 3 out if I wanted to. I get 3x cubed, 3 minus x to the 4th, pull out that 3, I get 4 minus 3x. To find the critical points, I want to... Is this thing ever defined? No, we're just adding and multiplying. That's never undefined. Does this thing ever equal 0? When do you equal 0? How do I know when something equals 0? There's a thing that you use a million times in algebra that you never say out loud why you use it. So I'm going to ask us to think real quick about why is this true? Why do I split this up now into separate things? The reason is, hey, name two numbers that when you multiply them, you get 0. Well, 0 times 5 is 0, but 0 times anything is 0, so that feels like cheating. Can you name two numbers that you can multiply to get 0 without cheating and using 0? No, you can't. That's called the zero product principle. The zero product principle is that if x times y equals 0, then one of those numbers had to be 0. In this case, I've got this times this times this times this equals 0. That means the only way that can happen is if one of these things equals 0. And 3 doesn't ever equal 0, hardly ever. So we're left with the other ones. When does x equal 0? When does 3 minus x equal 0? When does 4 minus 3x equal 0? I guess technically it's x cubed equals 0. I can use the principle and say, well, I have a bunch of x's here. The only way that if their product equals 0, then one of them equals 0, but they're all the same. So if one of them equals 0, they all do. The power of 3 and the power of 4 immediately don't matter. I got x equals 0 is a critical point. 3 minus x equals 0 gives me x equals 3 is a critical point. This gives me 4 equals 3x. I get x equals 4/3 is a critical point. Our critical points are x equals 0, x equals 3, and x equals 4/3. Alright, now to part B. Part B is finding the critical points tells you where the thing might have a local max or min, but I want to know, are these maxes, mins, or other? Let's classify these critical points as local maxes, local maxima, local minima, or stationary points. Stationary point is just a word for a critical point that wasn't a max or a min. That's the stop sign type of point. How do I figure out if my function has a max or a min or neither at these points? There's two ways to do it. The main one is called the first derivative test. The first derivative test works by make a sign chart of f prime of x and look at it to see the behavior. The other one's going to be called the second derivative test. We learned them first and second, but they're named that because one is about the first derivative and the other's about the second derivative. And we'll see the second derivative test briefly later. For now, all we have is the first derivative test. We want to make a sign chart of the derivative. What is a sign chart? You probably did this in some algebra class in your past, where I have a function. Here my function is the derivative. The thing I want to know the signs of are f prime of x. I have f prime of x written down in a bunch of different ways. The factored version is often the most convenient. F prime of x is 3x cubed times 3 minus x to the fourth times 4 minus 3x. And I want to understand what is this, when is the function positive, when is the function negative. If I know when the function is increasing, decreasing, that'll be enough to work out max min stuff. To figure out when is it positive, when is it negative, I view the line as a room. It goes from negative infinity on the left out to positive infinity on the right. And this room, this building is broken up into rooms. The places where I break it up are at the critical points, at the places where the thing equals 0 or is undefined. Those are at 0 and 3 and 4/3. I want to make sure and put them in order. This is supposed to be a number line. 4/3 is between 0 and 3. And those make up the walls inside this house. So I've now broken the house up into 4 rooms. And I want to know, what is the derivative doing in each of these rooms? I do this by taking test points. I need a number between 0 and negative infinity. I'll use negative 10. What is f prime of negative 10? I don't actually care what the value is. I only care whether it's positive or negative. And that means I get to skip some of the work. It's 3 times negative 10 cubed times 3 minus negative 10 to the 4th times 4 minus negative 30. 3 is a positive number. Negative 10 is negative, and when I cube it, it'll still be negative. 13 to the 4th is some big number, but it's positive. 4 plus 30 is positive. When I multiply all this out, it's going to be a positive times a negative times a positive times a positive is going to be negative. I've learned that at negative 10, the derivative is negative, and from that I get to conclude, like putting a drop of chocolate syrup in the milk, it spreads out everywhere, that the negative fills up the whole room. This is a big jump, and I want to spend a second thinking about it. How do I know just because I'm negative at negative 10, how does that mean I'm negative everywhere in this room? Well, if a function, here's negative 10, it's negative at this point. My graph is below the curve. If it ever went to above the curve, how do you get from below the curve to above the curve? Well, the only way you can do that is, well, I guess the easy way is you just cross through the x-axis. That's a place where y prime equals 0. I found all the places where y prime equals 0. That's what this list is. And none of them was between 0 and negative infinity. This is why it was important that I found all the critical points. Or you could also go to the other side by just being undefined. Like you can go down to negative infinity and come back from the other side. We've seen graphs that look like that before. That would be a place where the function's undefined. That would also be in my chart. I found all the places where the derivative is 0 or undefined, and those are the only opportunities a function has to switch between being positive and negative. If you switch from positive to negative, you had to either cross 0 or be undefined somewhere. So that's why this works. That's why I only need to do these 4 test points, is because you can't switch between positive and negative except at these points. You might switch between positive and negative at this point. We don't automatically know whether you do right now. So I still need to do the tests. Let's keep doing the tests. What's a number between 0 and 4/3? We're lucky and there's a whole number. I can do f prime of 1 is between 0 and 4/3. Sometimes you'll have to pick a fraction, and it sucks, but you're not actually evaluating everything, so that helps. It's 3 times 1 cubed times 3 minus 1 to the 4th times 4 minus 3 times 1. What are these? This is positive, this is positive, this is positive, this is positive, everything's positive. You multiply all together, you'll get a positive. The derivative is positive in this interval. What's going on between 4/3 and 2? We're lucky again, there's a whole number in there. I can take f prime of 2. It's 3 times 2 cubed times 3 minus 2 to the 4th times 4 minus 3 times 2. This will be positive, positive, positive. 4 minus 6 is negative. Positive, 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 negative makes a negative. The derivative is negative in this region. What's happening to the right of 3? I can ask what's f prime of 4? It's 3 times 4 cubed times 3 minus 4 to the 4th times 4 minus 3 times 4 is 12. That's positive. 4 cubed is positive. 3 minus 4 is negative 1, but when I raise that to the 4th, that'll be negative, 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 negative makes a positive. 4 minus 12 is negative. I get a negative here. This is basically enough to know what's going on with this function. The derivative is negative left of 0. What does it look like when your derivative is negative? The function was decreasing. After 0, we switched to increasing. If you were decreasing and then you switched to increasing, that's a local min. Now I'm increasing and I switch to decreasing. If you go from increasing to decreasing, that's a local max. And what's going on at 3? I was decreasing before and I was decreasing afterwards. This is one of those stationary stop sign points. X equals 3. is a stationary point. And here's the answer to their question. And I can get that from looking at this sign chart of these points. That's what the first derivative test is figure out when the derivative is positive and negative, and then you just sort of stare at that and read off, well then this is a local max, this is a local min. I guess I could make a chart of decrease, increase is a min, increase, decrease is a max. Increase, increase, or decrease, decrease is a stationary point. Those are not as useful. Or, I mean, I can, you just look at the picture in your head and that answers you. Let's talk about the second derivative test real quick. This thing is called the first derivative test. This particular problem is not a great one for the second derivative test. Let me grab a different problem for the second derivative test. Actually, let me state the second derivative test. For classifying critical points. The key question is, how hard is it to take the second derivative? In this particular example, we did the first derivative with the product rule and we got this is the first derivative. I wouldn't really want to take the derivative of that again. It would be a triple whammy product. You can, but I think making this sign chart was easier than taking a second derivative and knowing that I definitely got it right. Other functions, it's really easy to take the second derivative. Let's talk about the second derivative test real quick. The second derivative test works like this. If f prime at a point equals 0, then if the second derivative at that point is positive, what do I know about the second derivative being positive? That means concave up. That's the smiley type. If you have a critical point while you are smiling, then it's a local min. And if double prime of A is negative, that must be frowny. If you are frowny type and you have a critical point, that's a local max. And A is a local max. That's the end of the second derivative test. You should notice, though, that there's a missing point. There's a Goldilocks baby bear thing going on here. What happens if the second derivative is 0? You didn't say what happens there. If the second derivative is 0, we don't know. The second derivative test doesn't work in that case. It doesn't tell you anything. If you really need to know if it's a max or min, you're probably resorting to the first derivative test. Go back and make a sign chart of the first derivative to see what's going on. Let's try an example with that. Let's try x e to the x. Let's make it x e to the 3x. Let's find and classify the critical points using the second derivative test. We're going to need to take the derivative, we're going to need to take the second derivative. If you're not watching live, pause the video, try and take the first and second derivative of this. Come back and check if you got it right. If you're watching live, you try and go faster than me. Just go, do it. This is a product. I need to use the product rule. Derivative of the first, derivative of x is 1, times leave the second part alone, e to the 3x, plus leave the first part alone, x, derivative of the second part. Second part is e to the something. Derivative of e to the something is e to the leave the inside alone, times what's the derivative of the inside? Derivative of 3x is 3. 1 e to the 3x is e to the 3x. X times e to the 3x times 3. I'll put the 3 out front to make it look nicer. You don't need to do this simplifying. If this was an exam question, I would encourage you to put a box around this before you make a mistake. But I'm about to take another derivative, so it's worth it to clean it up if I can. I'm taking the second derivative. Derivative of e to the 3x is e to the, leave the inside alone, times derivative of the inside is 3. Plus, this one is a product, I need the product rule. Derivative of the first is 3. Leave this second part alone. Plus leave the first part alone, 3x, times derivative of the second part. Derivative of e to the 3x is e to the 3x times 3. This probably simplifies. I got 3e to the x plus another 3e to the x is going to make 6e to the x. Plus 3 times 3 is 9x e to the 3x. I want to know when the thing equals 0. I'm going to want to factor this. I might want to factor this also. They both have a common factor of e to the 3x I can factor out. This is going to be e to the 3x times 1 plus 3x. This was going to be e to the 3x times 6 plus 9x. I can also factor out the 3, but I don't care too much about the second derivative right now. Okay, finding the critical points is when does the derivative equal 0? I look at the derivative and I set when does g prime equal 0. When does that happen? That's when e to the 3x times 1 plus 3x equals 0. It's already factored. You will equal 0 when one of these things equals 0. E to the 3x equals 0, or 1 plus 3x equals 0. You're going to find problems like this where you're setting e to the something equals 0, and you're going to be thinking about natural logs and whatever. And in general, this is going to be more work than you need. Anything to the x, the graph of something to the x always looks like this. E to the anything, e to the stuff is always positive. Never 0. My phone buzzed. Is someone trying to talk during class? No, they are not. E to the something equals 0, that never happens. 1 plus 3x equals 0, that one does happen. 3x equals negative 1, x equals negative 1/3. So I immediately get the only critical point. Critical point is at x equals negative 1/3. Man, my stylus hasn't died at all today. I'm so happy my stylus is working, you guys. Now, how do I test my critical point? I use the second derivative. I take g double prime of negative 1/3. I don't actually care what the value is, just whether it's positive or negative. What is g double prime of negative 1/3? It's e to the 3 times negative 1/3, and it's going to be tempting to get really worked up about this, but remember, e to the stuff is positive. I don't really care what the value is, this is a positive. Times 6 plus 9 times negative 1/3. 9 times negative 1/3 is 3. I have a positive whatever times 6 minus 3 is positive. Positive times positive is positive. I get that g double prime of negative 1/3 is positive. If your second derivative is positive, I imagine it, concave up, smiley type, local min. I should give myself space to write this out. The only critical point is x equals negative 1/3, and g double prime of negative 1/3 is positive. So, x equals negative 1/3 is a local min. Cool. Cool. All right. I'm going to take a couple-minute break, and then I'll come back and start talking about 4.2. Let me double-check that 4.2 is about what I think it's about. Do I still have Wiley Plus open. I don't. Wiley Plus. Log in to my account. Chapter 4. Yeah, 4.2 is about inflection points. Cool. I'll be right back. Hey! I'm back. How's it going? 4.2 is about inflection points. Am I still streaming? I'm still streaming. Alright. Hey, there's me clicking on junk. And the short version of 4.2 is that it's a lot like 4.1. 4.1 we said for a local max or min, so if A is a local max or min, then f prime of A must equal 0. Or there's this other possibility where it's undefined, but we don't usually think about that. So if you have a local max or min, then the derivative equals 0, but just knowing that the derivative equals 0 there isn't enough. So we do a sign chart for f prime if we're doing the first derivative test. Really sloppy. The short version of 4.1 is that if you have a local max min, then the derivative must equal 0 there. So if you're looking for local extrema, take the derivative, set it equal to 0. Those are the points that might be local extrema. But just knowing the derivative equals 0 isn't enough to know it's a local max min. You do something to check if it actually is a max min, and to tell which it is if it is. And that might be the first or the second derivative test. For 4.2, it's basically the same thing about inflection points. If you are a local max or a local min, then you must be switching between increasing, decreasing, or vice versa. Well, if you're an inflection point, then you must be switching between concave up and concave down, or vice versa. That's what an inflection point is. So, if A is an inflection point, then the second derivative there must equal 0. Again, there's an or, it's undefined possibility. But if we weren't thinking about the first derivative version, we're definitely not thinking about the second derivative version. A place where f double prime equals 0 is called a subcritical point. Critical point is when the derivative equals 0. A subcritical point is when the second derivative equals 0. And just like with the first derivative, knowing that the second derivative equals 0 isn't enough to know that you actually are an inflection point. You do a test. And that test is probably... So we don't give them names. We're basically doing the first derivative test while looking at the second derivative. The first derivative test was look at the first derivative, see if it switches between positive and negative. That makes it a local max or a local min or whatever. We're going to do that on the second derivative. I don't know whether you would call this the first derivative test. It's the first derivative test applied to the second derivative. I don't know. I don't have there's no name for it because we only do the one. You could theoretically talk about the third derivative to figure out whether your second derivative, whether your subcritical point is a inflection point, but we don't ever actually do that. Let's do an example. Let's find all inflection points of y equals x e to the 3x. That's the same function we just worked with a second ago, so we've already got the derivatives worked out. And let's get those derivatives. Our original function is x e to the 3x. Our derivative was... do I still have it written down? It is 1 plus 3x e to the 3x. The second derivative was 6 plus 9x e to the 3x. And we're going to answer way more. If we're just caring about inflection points, all I really need to do is set the second derivative equal to 0. But I want to answer way more than this. There are a million questions that they could ask you, and you can get all of those questions answered by doing one big sign chart of the function and the derivative and the second derivative. I want to make one sign chart that includes when all three of these things might equal 0. When do u equal 0, and when do u equal 0, and when do u equal 0. And luckily I've got them all factored. This will equal 0 when x equals 0, or e to the 3x equals 0. E to the something is never 0. So x equals 0 is the only a place where the y value is 0 is an x-intercept. I set this equal to 0, I get 1 plus 3x equals 0. Or e to the 3x equals 0, but that never equals 0, so I get x equals negative 1/3 is the only critical point. Set this equal to 0, I get 6 plus 9x equals 0, or e to the 3x equals 0. That never equals 0, so I get 9x equals negative 6 divided by 9, x equals negative 6 over 9, that's negative 2/3. X equals negative 2/3 is the only subcritical point. I got these three relevant types of points from caring about when does y equal 0, when does y prime equal 0, when does y double prime equal 0. I build a sign chart. I'm going to build, I talked about the first sign chart as being a building. This one I'm going to build a 3-story building that's going to have all the information about all of the functions we care about. The three relevant points that I want to include on my x-axis are 0, negative 1/3, negative 2/3. 0 is the biggest of those. Negative 2/3 is the least of those. Negative 1/3 is the middle of those. It's going to be tempting to cut the world up into 12 rooms, but we don't need to do all that. 0 is not going to be a relevant point for all three functions. Y, that's y. This is y prime. This is y double prime. 0 was only a wall for the original function. So the third floor is cut into 2 rooms. The derivative equaled 0 at negative 1/3. I got a 0 here. I'm putting the circle here as indicating the number 0, like a plus is for positive and minus is for negative. That 0 is saying this is a place where y prime equals 0. And here is the only place where y double prime equals 0. And I fill these in just like with a regular sign chart. I need to pick a point in this region and plug it into y double prime to figure out whether this region is going to be plus or minus. Can I figure that out? I take a number left of negative 2/3. I'll take y double prime of negative 1 is 6 plus 9 times negative 1 times e to the something. I don't care what it is because that's going to be a positive. 6 minus 9 is negative times positive is negative. I got that it's negative here. I want to plug in any number to the right of negative 2/3. 0 is a pretty easy number to plug into most stuff. I'll plug that in. What's y double prime of 0? Y double prime of 0 is 6 plus 9 times 0 times e to the whatever. I got a positive times a positive. We're going to be positive at 0. That means this is all positive. Cool. All right. Usually, I think always, the bottom row is enough to know what's going on the row above it. What I'm about to do is a cool trick that will save us having to plug in this point and plug in this point and plug in this point and plug in this point. This is optional. It's saving us the 4 plugging ins of points, but you can do it all in your head, so I think it's worth thinking about. What's going on here? I have a place where something equals 0, here it's y prime, and its derivative is positive. When I think about what y prime must look like, it's passing through 0, and its derivative is positive. I am increasing through 0. If you pass through 0 in an increasing way, you must have been negative to the left and positive to the right. That immediately lets me fill in these 2 squares. And now I can do the exact same thing here. Y is passing through 0, and its derivative is positive. So it must have been negative on the left and positive on the right. Neg. Pause. This is just saving us the work of plugging 4 points into 4 functions. To figure out that this is negative, I need to pick a number left of negative 1/3, plug it into y prime, and see if it's negative or positive, and apparently we will end up with a negative. So we're not saving that much work, but it's, I think, a smart way to think about things. Like, keeping these pictures in your head is good. What do we conclude? They told us to find the inflection points. I found that negative 2/3 was the only subcritical point. It's the only point that might be an inflection point. And now from this chart, I can tell it actually is an inflection point, because the second derivative went from negative to positive. We were concave down, and now we are concave up. So switching concavity is what it takes for an inflection point. X equals negative 2/3 is the only inflection point. We knew it might be an inflection point, and we've now confirmed that it is. I can answer other questions. X equals negative 1/3 is a local min. How come? Because I was decreasing and then I switched to increasing. That makes you a min. I knew I was decreasing because the first derivative was negative then positive. And x equals 0 is the only x-intercept. What else can we ask? The problem might ask, when is the function increasing, decreasing, concave up, concave down? These are things we can answer. I know you're increasing when the derivative is positive, decreasing when the derivative is negative, concave up when the second derivative is positive, concave down when the second derivative is negative. This chart has all that information. The graph is increasing on the first derivative is positive here, so that's negative 1/3 to plus infinity. When are you decreasing? That's when the first derivative is negative. That's here. So that's negative infinity to negative 1/3. When are you concave up? That's when the second derivative is positive, so that's from negative 2/3 to plus infinity. When are we concave down? That's when the second derivative is negative. That's negative infinity to negative 2/3. Cool. What else do I want to know? I might want to know, so increasing, decreasing, concave up, concave down. Yeah, these are like the facts that they might ask. I can't think of any other versions of the question that you would read off the chart other than sketch a good graph with this information. Well, this is one of the things that you become really good at real fast if you are doing calculus problems like this. Did I say fast? It's not fast, it's slow as hell. But it's a thing that was very difficult to do by hand before calculus, and now is pretty good with calculus. Finding local extrema was difficult. Finding inflection points is difficult. But I can now put together a graph that has all this information pretty reasonably accurately. I care about these points, 0, negative 1/3, to negative 2/3, so I would like for those points to be reflected accurately on my graph. So I'll work out what is f of 0, what is f of negative 1/3, what is f of negative 2/3. I'm not doing this as test points to fill in my sign chart. I'm doing this because these are points that I want to have correct on my graph. These are important points. I would like to know the correct y values to graph these points very well. F of 0, our function was f of x is x e to the 3x. F of 0 is 0, is easy. F of negative 1/3 is negative 1/3 e to the 3 times negative 1/3. It's negative 1/3 e to the negative 1. That's, dear calculator, what is negative 1/3 third e to the negative 1 is negative 0.12. F of negative 2/3 is negative 2/3 e to the 3 times negative 2/3, negative 2/3 e to the negative 2, which is, hey calculator, what is negative 2/3 e to the negative 2? I'm getting negative 0.09. O2. So if I want a good graph, I should include these points. Let's copy this junk over. I'm going to copy our sign chart over. So I got these 3 dots. I got 0, 0. Let's go negative 1/3, negative 2/3, negative 1. So negative 1/3 is a relevant point. I need to go as low as negative 0.12. I have 1, 2, 3, 4, 5, 6 tick marks. Let's make each of these negative 0.02, 0.04, 0.06, 0.08, 0.10, 0.12. We found that at negative 1/3 our value was just a little bit less than negative 0.12. I guess it should be an eighth of the way to the next line below it. And then at negative 2/3 we had a value of negative 0.09 almost exactly. So I have a dot here, I have a dot here, and I have a dot here. So right now I know these 3 dots. The next thing I want to do is connect these dots using the correct shapes of curve. What do I mean by shape of curve? I told you earlier that increasing, decreasing, concave up, concave down leads to like 4 possibilities. And they are these, depending on what you are, concave up, concave down, whatever. I want to think about, in each interval, which of these 4 shapes is going on. Left of negative 2/3. Second derivative is negative, that says concave down. First derivative is negative, that says decreasing. Concave down and decreasing adds up to this shape. I want to be doing this shape left of negative 2/3. Between negative 2/3 and negative 1/3 we are concave up, but still decreasing. That's going to be this shape. This negative 2/3 is going to be our inflection point where it switches from concave up to concave down. Between negative 1/3 and 0 we are concave up still, and we are increasing. The increasing half of concave up is this. What's happening to the right of 0? We are increasing and concave up. That's going to be this shape. Hey, these 2 are the same shape. It will be tempting to make a graph that goes concave up increasing, concave up increasing. That's a mistake. The thing to keep in mind is that this point 0 was an intercept, isn't changing anything about the graph. These 2 should smush together into one big concave up increasing thing that just happens to pass through this point at that point. I can't hit the point as I go. So I just want to be increasing concave up to the right of negative 1/3. But I want to actually pass through that dot. Something like that. Between here and here, our graph should be decreasing concave up. And to the left of this point, we should be decreasing concave down. It can be tempting to draw it like this, but remember it's not going to cross the x-axis because we found all the intercepts. We found when y equaled 0. It's not going to be able to pass the x-axis without being 0 again, and we found all the times that it equals 0. The graph should look something like this. Let's graph it and see. What was our function? Our function was y equals x e to the 3x. And even better than just graphing it and seeing if it looks right, I can draw a window that matches this window exactly and see if it, matches exactly. I drew this How low does my min go? This was negative 1/3, 2/3, negative 1. I guess that would be about negative 4/3 here. I'll make my x-min be negative 1.33. The maximum x value is positive 1/3. The scale, this is how often to draw a tick mark. I had a tick mark at every 1/3, so I'll call that 1/3. How low do the y values go? My lowest y value is a little less than 0.12. Let's make it negative 0.14 is where the next line would have been. What's my maximum y value? I've got 3 lines up, and if each one is 0.02, then our max will be at 0.06. Where did I put a tick mark for the y's? I drew tick marks every 0.02. Does this look right? Ooh, ooh, ooh. Yes! Man, I love that feeling. We nailed it. Check it out, man. This looks exactly like the thing we drew. Nailed it. I hate Instagram for ruining the phrase nailed it. I want to use the word nailed it non-ironically when we actually did nail it. And we did nail it. I don't only want to use it when we screwed things up. Okay, that's basically it for 4.2. I need to look at the homework and see if there's any topics I've missed. I'm probably going to record a video tonight. I'll announce it on the chat when I do, but I'm a little bit behind. I started late today and I'm ending a little early today. I just got a message that one of my bosses is freaking out over a different thing about my job I need to go deal with. But I'm going to record some tonight. You don't need to watch live tonight. You don't ever need to watch live, but if you want to, you can. And then pretty soon I'm going to be just linking to all the videos I made at the end of last semester. And instead of recording live, I'll just be taking homework questions live if anyone ever wants to ask me a homework question. I never get questions from you guys. If you have homework questions you want me to talk about, let me know. I'm around. I gave you my number to text me. I'm not getting anything. Does that mean everyone's doing great? I don't know. I'm feeling lost without having a classroom to look out at and see if people are freaking out or not. I'll see you guys later, either tonight or tomorrow, whenever I see you.